Hello, it's Hasna Mustafa. Good morning, everybody. Thanks for your time today. I'm happy to be with you today in this webinar for Internet of Things and for computing. So for Internet of Things, let's start by seeing how the connected objects are exploding and starting from 1 million of connected objects early 90s when we were limited to PCs, and how this is evolving by time until reaching 50 billion, or expected to reach 50 billion and more connected objects by 2020. These includes different types of devices which were in there before. More than PCs, there are a lot of small devices, there are a lot of personal devices, other devices for manufacturing, for transportation, for a lot of different segments. So if we look at the key IoT market segments, and especially related to the segments that started with the embedded systems and moving forward and coping with IoT right now, we have smart buildings, smart homes, automotive and transportation. Manufacturing also is a big segment, which includes the energy and oil segments. The retail segment is another segment. Agriculture, IoT starts to appear. And we have video surveillance, which is a segment that's considered as a transverse segment, serving most of these IoT segments and contributing with a big amount of heavy traffic from video. If we have more insights on smart building segments, especially giving an idea on the US market opportunity, we have about 5 million commercial and industrial buildings, and the spending is about $200 billion each year on energy in this commercial and industrial buildings. So the energy consumption is about 70% effective. And there is a waste which is declared by the Department of Energy, which is about $60 billion each year. That's for the energy waste. If we look at the environment, we have 45% of the CO2 emissions that comes from commercial and industrial buildings. If we do 10% improvements only in this emission, this is equivalent to 30 million cars. So you can imagine how we can save a lot of energy and save the environment only from this segment, which is the smart building segments. Without IoT, this is hard to do. So with IoT, there are a lot of solutions which allows energy saving, which allows controlling and monitoring lights and heat and temperature in smart buildings, and water consumption, a lot of energy resources. We also have about 3 million residential buildings, among them 18 million residences, and before 1970 there was 85, these were 85%, and it starts to be 94%, and this increased until year 2000. For IoT solutions here, we have a lot of products which is being sold to smart buildings and homes, mainly using gateways or IoT gateways. I will give more details on the IoT gateways in the later slides, but just to give an idea, for gateway forecast in this big market, in New York City only, there is about 12 kilo units of gateways, which is forecasted for 3 properties among these residential buildings, which means that there is a big opportunity for IoT gateways in smart homes, on smart buildings. Another insights is on the retail segment, because this point is a kind of new, which is vending machines. If we look at the retail, first thing which comes into our mind is the shops and the stores. But within the retail segment, we're also dealing with vending machines, like coffee vending machines in this picture. So vending machines is being a big opportunity right now as connected objects, and there are solutions which are being sold right now, software solutions to monitor several points in the vending machines, to monitor the boiler scaling leakage, filter efficiency, gear pump degradation, the aqua valve malfunction, flow meter malfunction, or even change in the grinder settings, which can degrade the coffee taste. So monitoring these, so the importance of having these machines connected is not only to test continuously the health of the machine, but also to test the quality of the coffee which is being served from this machine. So several coffee makers right now, they are seeking IoT solutions for vending machines, and there are some solutions which are in place now. If we look at in this market segment, what is the IoT value chain? We have hardware, which is the initial thoughts in the mindset of people. We have connectivity to connect the machines, to connect the unconnected things, and we have the value-added services. Surprisingly, hardware constitutes 33% only of the value chain. Connectivity constitutes 20%, and the rest is coming from value-added services, which means that there is a huge opportunity that IoT gives for value-added services. If we don't have value-added services, we cannot make good and usable IoT solutions. What are these value-added services, or how they can be? This comes from the connected device platform to make the device a connected platform that can be reached remotely, to do device management remotely, to provide several opportunities for connectivity through different network interfaces. Device cloud is another added value. Connect the device to a cloud service. Application development, of course, which requires APIs for application developers, system integration, and analytics, which is a huge value-added service, which allows making use of big data. The real use of big data cannot be done without efficient analytics, and there are several professional services. So we call the value-added services application enablement platform because that's what enables IoT solutions with the existing hardware. If we look at all this explosion of connected devices, the expected 50 billions by the coming years, we can say that the good news is that everything is becoming data. Everything is becoming data, meaning it's good. We have a lot of data, we have more information, but this doesn't come at the expense of nothing. There are a lot of challenges, as we will see. So we have the acquisition of data. So it's all about data. We need a lot of sensors. We need a lot of small devices, as well as network devices to talk to these small devices and do the data acquisition. And we have analytics that should run on this data to have meaningful information. And we should end up by an action making use of this data and making use of the result of analytics. There should be an action, whether controlling some devices, whether enhancing a service. If we see this picture, we have different IoT segments generating different data. So access to this different data through at different level of the network, starting from an IoT gateway and going to the edge network until the data center. This can enable a plethora of services making use of this big data. But as it is a good news also, it's a bad news. The bad news is that everything is becoming data. And why? For these different challenges. When we have lot of data, which we call big data. We have first challenge that we face, how to turn this big data into small data. We cannot deal with this big data. We need to extract what we need from the big data. So we're facing the challenge of turning big data into small data. Another challenge is moving the data. Moving massive amounts of data is potentially expensive, and at a certain point of time, our network infrastructure will be a challenge in this domain. Another challenge is the security. This data, most of the time, is sensitive data when coming from factories, from industrial environment, from even medical care services. So we will need new security protocols. We will need a lot of security operations to guarantee the maximum security on this data. So we're facing these challenges. How can we minimize these challenges or mitigate it as much as we can? If we look at the fog computing and the edge computing for IoT big data, it's a very compelling solution and being discussed this day to deal with transforming big data into small data, and also to help in this problem of moving big data. Let's see more what is that. So if we take this picture again, we see instead of focusing on this backend data center, which is sitting in the cloud as processing and as the analytics, and let's move the processing resources to the edge. And that's not a concept which comes like that. There are a lot of analysis and analytics which and forecasts which say that by year 2018, 40% of the IoT created data will be stored, processed, analyzed, and acted upon closest to or at the edge of the network. So moving processing and storage to the edge of the network is a very promising trend, which is being highly discussed. A lot of standardization bodies right now are created and are working on that, like the Open Fog Consortium, which is recently constituted to consider IoT fog solutions. We talk more on that. And there is also the mobile edge compute. We talk more on that in the coming slides, which is being discussed within the ETSI, European Telecommunication Standard Institute, and industry specification groups. They are speaking about and standardizing the mobile edge compute. So that's a current trend and is very useful for IoT. If we look at network infrastructure tenets for IoT in 5G, if we look at 5G, which is the future and which is expected by year 2020, 5G is talking about network functions, about aggregation, about data aggregation at the network edge, and is considering IoT as a specific use case and how to prepare for network infrastructure that matches the IoT requirements. So in the coming generation of networks like 5G networks or even 4.5 generation, we have diversity of communication technology coming from IoT and diversity of traffic, because IoT comes not only with diversity of communication technology from the billion of connected devices, but the traffic itself is diverse. Traffic can be 3 bytes of data coming from smart metering, for example, and can reach a big volume of data coming from video surveillance. So there is this kind of diverse nature of traffic. So IoT traffic aggregation at different level in the network is required. We cannot deal with this whole volume of traffic through bypassing all this traffic constantly all the time to the cloud. There is a need for a different level of aggregation in the network. So this requires cloud migration to the network edge and more closure to data sources, instead of counting only on the cloud at the backend data center. This is being migrated now to the network edge to create a kind of cluster of compute and storage resources and the components that constitute the clusters of compute and storage resources can be IoT gateways, can be fog elements. I'll explain more on that. Can be mobile edge compute servers. I'll explain more on that. This gives an opportunity not only to offload the network resources but to the edge, but also to monetize new hardware and new software and new devices management and also resources orchestration at the edge cloud. So this will create new business model. Operators will have a new monetization means. If we have an idea on cloud migration to the edge and the why for cloud migration to the edge, there are several reasons. We have much lower bandwidth and cost will be needed. Availability anywhere and anytime, meaning if the data coming from IoT devices talks with an edge device, it can reach this edge device easier and anywhere and anytime than waiting to communicate with the backend cloud. For real-time functionalities, this will ensure better latency. Also, easier adoption of new technologies, meaning what if there are new technologies, it's easy to adopt these new technologies on edge devices than to do it on the back-end data center. On heavy devices. Edge devices are smaller devices. They can be replaced easily. They can be expanded easier. If we look at this figure, that gives a cost idea on a solution based on cloud only. That's for 3 years cost and based on edge plus cloud. We see a huge amount of saving which results from using the edge plus cloud instead of cloud only, which is a tempting approach, of course. What is a flagship application for edge processing? It's video. That's really a flagship application. We can see that video in IoT is exploding as the connected devices are exploding and reaching billions of devices. Video traffic also is exploding, and there are a lot of expectations by analysts on huge numbers of connected cameras in the coming years. So the forecast is for a total of 129 yottabytes of video traffic generated by 2020 from IoT. 41% of them will come from sensors and 59% will come from cameras. Meaning what? Meaning that by year 2020, more than half of the IoT traffic will come from cameras. There is also a prediction on the huge increase in the number of IP network cameras in the coming years. So that image gives an idea on how video and image data are increasing and how they will become more than half of the total IoT traffic by year 2020. If we look at the top video or vision use cases, we have surveillance. Just for surveillance, we have access control to face detection or face recognition for giving access control to someone. We have traffic surveillance in roads. We have ADAS, which is in vehicles, which is assisted drivers, advanced driver assisted systems, and we have privacy preserved monitoring. All these are use cases which uses video and which uses complex processing that requires efficient analytics like face detection, face recognition, face identification, a lot of other features like LBR, license plate recognition for vehicles, or OCR, object character recognition for object recognition. So we look at video from from 2 points, from the heavy traffic generated by video and also from the heavy processing required for video analytics. And these are just simple examples on the dominant features that we are having in video and vision analytic algorithms. This will show more the need for edge processing, the need for edge analytics. How cloud migration to the edge? What are the current trends today? We have two trends. We have mobile edge compute and we have fog computing. These are the two trends which are being discussed, which are being worked by standardization right now, and for which some solutions started to take place. Here that's just an image to show between the back-end cloud or the back-end computing at the cloud or edge computing. How can we save in terms of latency? Latency increases, of course, when we go away from the data sources. If we do edge computing next to the data sources, we can ensure lesser latency. Same for the real-time analytics. Analytics are more real-time when they are done closer to the data sources. If we look at mobile edge compute, what is mobile edge compute? Mobile edge compute, maybe some of you are aware of it. It's something, or it's a server. It starts by server, MEC, or mobile edge compute server, which is co-located at the access level with eNode B, with the cellular access network. So it's a server co-located with eNode B and intercepting the path between the access and between the mobile core network. And this server has its applications and services implemented through virtualization, through network functions virtualization, and it provides what they call edge cloud. So instead of traversing the whole network and going to the back-end cloud, the traffic which crosses the eNode B, it meets the MEC server and it can reside here at the MEC server for processing, for analytics, and even for some services that can be provided at the edge. What's the opportunity? The opportunity is to, it's a very promising opportunity for IoT and for even Internet of Everything. One should notice that the MEC, when it started several years ago within the ITSC ISG group. ISG is Industrial Specific Group. Or industrial specification group. It started before the boom of IoT. So it started initially to enable billions of connected mobile devices, which is the handheld mobile devices. It started to provide value-added services to mobile devices, to mobile users, like video streaming with better quality, with more real-time, augmented reality services, and with IoT, MEC is taking a kind of a new position to serve IoT ecosystem. If we look at fog compute, just to make a note here, MEC is being a standard now with several milestones that are being accomplished at the ITSC ISG group. Coming to fog computing is being discussed by different actors of IoT, and the standard hosting the fog computing right now, the official standard is the Open Fog Consortium. It has been recently created, and Intel is one of the core members initiating this effort. There is ARM also, which is a member, Cisco and Dell, and there is Microsoft, and from academics there is Princeton University, which is driving a lot of efforts also with these industrial actors. So it's an pretty open, it's a pretty new activity for the Open Fog Consortium, and the idea is to derive an architecture for network of fog nodes. They call it fog nodes, that extends the cloud to the edge, and to enable new networking, compute and storage platform, and to leverage the MEC server. So they are building on what the MEC standard is doing, and MEC will be leveraged in the fog computing world. So if we have here just a picture which might which might be not so recent as it doesn't have 5G here. So we have that's devices, and that should be billions in the coming years. That's the devices world with the different smart things and even smart networks, wireless sensor networks. And we have the intelligence fog, which lies or which is situated between the devices and between the core network. So it extends the cloud. If we have the backend cloud here, so the fog extends the cloud domain really to the edge of the network and very close to the data sources. And it allows compute, it allows processing, it allows storage at the edge of the network. So if we talk about some platforms or some solutions for fog and edge compute, sorry for that. One thing I can mention is Intel Gateway Solutions for IoT. What is Intel Gateway Solutions? Intel Gateway Solutions are a gateway, which is, we can call it a plug and play gateway, the hardware with the whole software stack allowing it to work. So the Intel Gateway Solution sits in the local network closer to the data sources, and it's being currently shipped for transportation, for energy solution, for industry solution, and it allows data aggregation and some processing and communication with the cloud. So what does it provide? It provides key building block to enable connectivity of legacy industrial devices and next generation intelligent infrastructure to the IoT. It integrates technologies and protocols for networking, for embedded control, for security, and for easy manageability. All the software stack for security, for manageability is shipped with the gateway, and it provides connectivity to the cloud and to the sensors. And it allows intelligent processing and local compute. So there is a local compute which takes place here and sending to the cloud. So breaking big data into small data. So what will be sent to the cloud is small data at the end, which is the result of analytics. That's an idea on the different products which exist for Intel IoT Gateway, different series, starting from Quark platform and Atom platform, and even going to Core and Xeon, which is coming. This one is what available in the market right now, but in the pipeline there is Core platforms and Xeon platforms, which will be in the market soon. And these are the different software stacks which is shipped. That's for the gateway. If we look at the MEC server side, there is Intel Network Edge Virtualization SDK, NEV SDK. And NEV SDK, what does it provide? It provides the MEC, the Mobile Edge Compute reference libraries, which provide S1 traffic information to virtual machines. S1 traffic is the traffic which is coming from eNode B. In fact, MEC server speaks with the eNode B through the S1 interface in 3GPP. And so the MEC reference libraries receive the traffic from the S1 interface and connected to the virtual machines sitting on the MEC server. And it allows real-time virtualization, accelerated virtual switch, and an open standard-based solution also with scalability and interoperability. So it works on Atom platforms, it works on Xeon platforms. So it gives developers the opportunity to use and to deploy with an MEC server and to put it to operation. Optimized to Intel hardware, of course. If we look at some key use cases for fog computing, we have the connected cars and the V2X. Currently, there is active efforts from different industrials on connected cars and V2X, which is V2X, vehicle to cloud, vehicle to infrastructure, and vehicle to vehicle even, which is expected by year 2020 with the 5G standard. So there is a very big growth in the connected car market right now, and 5G industry even is moving from connected cars to autonomous driving cars. Is expected by 5G timeframe to allow self-driving, to allow automated telematics like traffic and road weather condition alerts, to allow infotainment services as music streaming, remote and automated management for the software and firmware, accident reports in real time. So all this to have autonomous driving, which is expected by 2020 timeframe. We cannot rely on the cloud. We need compute resources next to the vehicle, and so here the fog and edge compute is a key tenant for V2X. Earlier, if you're familiar with the GSRC standard, which is direct short range communication, which is with the IEEE 802.11p, they spoke about RSU or roadside unit. So the notion of roadside unit was discussed earlier, and now we can say that this roadside unit can be a part of the fog ecosystem as a fog element. The roadside unit can be a fog element for compute, for processing, for communication with vehicles. So if we take one use case for vehicles, we have road traffic and vehicle surveillance. We're not speaking about connected vehicles now, we're not speaking about autonomous vehicle, we're speaking about the vehicles of today. If we want to do a kind of traffic and vehicle surveillance in an autonomous way, video surveillance is taking place right now in some cities, and so we can see cameras on the roads, but we wonder how these cameras work. Do they work in an efficient way? And what I learned is that most of these cameras are put there just to let the driver disciplined, and it's very hard to make them work and to make them operate in covering all the roads. So if we have if we count on fog computing and mobile edge computing, this scenario can be realized and can be realized easily. So the cameras can be easily connected to a gateway, an IoT gateway, and we have some trials, field trials testing this service. And the IoT gateway can continuously collect the video feeds from the cameras, and the IoT gateway is proximate to the cameras. And then the IoT gateway sends to the MEC server, which is in its region, whether the whole video feed or after aggregation, or the IoT gateway can run some analytics and send to the MEC server the result of the analytics. And the analytics can be license plate recognition, can be road traffic, how dense is the traffic itself, and this can happen in a smooth and automated way. Better than using a cloud solution. Using a back-end cloud solution can be very, very expensive for such service. If we look at another use case, which is ADAS on roads. ADAS, usually we have the advanced driver assisted services, which is in high-end cars. High-end cars right now, they are all equipped with ADAS system. But if we look for an affordable and community ADAS service on roads, which is a compelling thing, this can happen through edge compute with video surveillance. Meaning what? Meaning that instead of having, that's a car which is not a high-end car, it doesn't have an ADAS system, but it can use a road-assisted ADAS system. Cameras on roads, if we take lane departure as an example, cameras on roads, taking video capture continuously, and the video feeds are sent to the IoT gateway. The IoT gateway itself can run the analytics to detect the lane departure, or can send the video feed completely to the MEC for detecting lane departure. And if the lane departure is detected, then the driver receives a warning. This warning can come on his mobile phone, or there can be a small piece of dongle with a cellular connectivity in this car, which can cost a little amount of money compared to an ADAS system in a high-end car, and the driver receives a warning. So that's a kind of service that can be deployed using edge and fog compute. Another thing is self and smart parking for autonomous vehicles. That's more advanced service. When we come to the era of autonomous vehicles, we will face a problem of parking. Autonomous vehicles meaning unmanned vehicles, meaning no driver. So when we're driving, we can manage to park our cars, but a vehicle with no driver needs some assisted operation for parking. So how this can happen? We need an infrastructure unit. We need an infrastructure unit. We cannot count on the cloud to be able to guide the vehicle how to park or where to park, because the cloud is far from the parking lot. But if we have an IoT gateway, which is considered as an infrastructure unit, at the parking entrance, and this IoT gateway can have all the information continuously on the available parking lot. So when the autonomous vehicle enters the smart parking, it receives from the infrastructure unit information on the available parking lot, and so the autonomous driving vehicles are equipped with navigation, intelligent navigation. So they take just the XYZ from this infrastructure unit of the available parking lot, and they can navigate to it. In terms of payment, payment also will be paying for parking by an autonomous vehicle. How this can happen? The MEC server can be of help here, meaning when the autonomous driving vehicle enters the smart parking, the entrance time and maybe the LPR of the vehicle are sent to the MEC server, which identify together with the time of entrance, and at the exit, the time of exit is also transmitted, and here there will be the duration of this vehicle, which is noticed, and automatic billing can happen after that with the banking system. What's more here is multimedia and video streaming in autonomous vehicles or autonomous cars. We're speaking of autonomous cars. Autonomous cars meaning passengers, meaning unmanned vehicles, but there are passengers. Passengers will not be driving, so there is a need for entertainment, and even we're speaking of multimedia inside the cars on multiple screens, and we're looking even now for solutions for connectivity, for streaming video on multiple screens for autonomous vehicles. So here, if we look at continuous video streaming from the cloud to the screens, to the seat screens, it would be a very expensive information. But the MEC server can be helpful here to continuously stream video to vehicles. The video would be received by the IVI system, and the IVI system inside IVI is in-vehicle infotainment system, and the IVI system will internally stream the video through another Wi-Fi solution inside the vehicle. But video coming from the cloud is better to come from the edge cloud, from an MEC server here, to save resources. Another thing here is the e-health, which is becoming surveillance in clinics, for example. That's a use case which comes into the play, and we have different discussions with hospitals, with healthcare providers to see the opportunity of automating the monitoring and surveillance of patients through IoT solutions. And here, if we look at the patient's room in a hospital or in a clinic, we need two things. We need to continuously monitor the patient, especially those in a critical status, and also have a control to the different equipments in the patient's room. So if we count on the cloud, it will be a hectic operation in terms of resources and also sensitivity of the information which is being transmitted. So what can be a useful solution is having gateways also as fog elements, receiving video streams from cameras in each patient's room, and running a part of analytics here or even another part in the MEC server, and notifying the staff whenever there is a problem. That's for the surveillance through video, but more than that, we can have a control also, control flow from the remote staff to any of the patients through for controlling the different devices in the room. So here we need a reliable communication, we need a real time, we need a low latency communication. If we want to stop a device or to put on a device, we need this to happen real time. So it can be easy deployed by the edge devices than bypassing by the cloud. Retail also stores and promotions, pushing promotions to customers in stores is becoming an appealing use case, and there are a lot of digital signage devices which is being available more and more in retail. But even with digital signage, we cannot attract the stores customers so often. We cannot ensure if they can always read the digital signage or not. So an idea also is, and this happens in retail, by the way, there are solutions which has cameras and which does face recognition, not face recognition, gender recognition, age recognition, so to keep privacy, and based on the age and gender, there is a statistics which goes to the retail owner to know the demography of the customers. That's what happens today. But we can do more, meaning what? Meaning based on the demography of the customers, these customers can receive coupons on their cell phones, for example. So this solution can be deployed through an edge solution, an IoT gateway, which takes the video streams from and do age recognition, gender recognition. Until here, this part is there now. We have IoT gateways in stores which captures video, which takes the video feeds and do age and gender recognition just for statistics information, not more. How can we add more? This statistic information can go to the MEC server, and the MEC server can push coupons back to the customer based on the age and based on the gender. I think that's all what I have. I hope that it gave you, and I want also to see if you have questions, if you have to leave some minutes for questions. Okay, I'll check now to see if there are questions. Okay, I have 80% of what? I return back to this slide. They say the for computing, okay. Okay, so there is a question on the difference between the MEC and the fog computing. Okay, we don't need to compare them. MEC was there since several years and before the boom of IoT, and it was for a specific purpose, which is enhancing services over telcos network, and so creating a sort of processing at the access level to save resources, to help operators to save network resources, that and to enable better user experience for mobile users. That was the idea of MEC. With IoT, MEC now is covering IoT ecosystem also with this same purpose, but instead of being limited to mobile users, is for all IoT devices. When FOG came, Open Fog Consortium and the notion of fog computing, fog is speaking about pushing the resources closer or extending the cloud resources closer to the sources of data. This can be the MEC, and more than the MEC, more to the edge, meaning going more to the edge, creating, if we go to this, one of the figures can show more how this can evolve. Here, for example, we look at the cloud as the notion of pushing the cloud from the data center down until being as close as possible to the sources of data that can come from a car, from an industrial environment, from home. So IoT gateway is an example of a fog element. Okay, that's not an MEC. That's really in the local network and in the proximity of these devices. So that's a fog element. MEC is the access level. Fog includes extends the cloud, and it can cover the access level and lower than the access level, which we call pre-access level even, as the gateways. You can think of, for vehicles, we can have an equivalent here, roadside unit, which is pre-access, which is before the E-Node B. The vehicle itself is equipped with a gateway, which is, and it is being shipped right now for high-end vehicles are equipped with gateways, which for a lot of processing and intelligent features, like the ADAS systems, and so that's considered as a fog element. So think of a fog as extending the cloud to cover the whole network infrastructure, reaching the access, which can be here the access and the MEC server, and going down pre-access even. So hope that this clarified, but I would say there's no need to say what is this versus that, because MEC has a specific scope and fog is using MEC, is leveraging MEC, but is extending the whole notion of edge processing. There was another question on network function virtualization. So network function network function virtualization, I spoke about it with the MEC, and also in this big picture. Of course, there is a big opportunity for software-defined network and network function virtualization. That's the whole idea of MEC, and even Open Fog Consortium are speaking about that, are speaking about virtual machines and software-defined features for the network and virtualized switches. So the idea is IoT is more and more requiring network function virtualization and for edge compute. Not sure if we can take one more question. I think the presentation, someone asked if the presentation can be sent. Yes, I think with the organizer, the materials will be ready to deliver, no problem. Egyptian market, IoT impact on Egyptian market. Yes, okay, that's a good question, a very good one. And actually, I had some discussions with some companies, mainly around video surveillance. And so Avid Beam company, maybe you spoke about, you spoke with Avid Beam, I'm sure, before. So the idea is for the Egyptian market, I think video surveillance is a very compelling market because video surveillance is required. We need video surveillance in any market, any segment. But in Egypt, there will be the bottleneck, the network bottleneck problem will be more critical. So how to deal with with the network bottleneck. If we have, for example, take a city like Cairo and try to deploy video surveillance in different areas in Cairo, touristic areas, or any other selected kind of areas, and let's count the number of cameras, IP cameras that we will deploy, and the video feeds if it's 24 hours a day. So there will be a big volume of data. How can we send this data to the video management system on the cloud? That would be something very expensive. Maybe it wouldn't be real time. So here, edge and fog compute is a very useful approach to connect several cameras to one gateway, and this gateway can filter the video, can run analytics, and can send to the cloud what's needed, the relevant scenes, or even the result of this video if there is something critical or not. So that will be the problem of transforming big data into small data, and for a heavy volume use case. Other than that, I think that okay, how can we say that? Asset tracking. Asset tracking is another very good opportunity also, because asset tracking, the solution that we deployed right now, these are not expensive solutions. It's a small piece of sensor which is installed in trucks, and it has a 2G even connectivity to speak with the back-end network, and for sending tracking information. For example, how many trucks entered, and the ID is this sensor can be associated with an RFID to identify the truck even. So that's a solution which is not an expensive one, which allows the automation for asset tracking. What more I can see? Agriculture IoT. Agriculture IoT right now is not an expensive solution. Solutions are not expensive because it requires, I don't know, something like $1 sensor or so that can be installed in the fields in different areas to test water leakage, for example, or to test dryness, to test even insect problems or so, and send this information. This information can be sent to the cloud here because it's really small information through a 2G connectivity, which is not an expensive one. What else? Future of fog computing in developing countries. Okay, that's a very good question also. It comes with something which is good, which is low cost. It provides low cost. It's not only saving network resources, but it comes with a low cost. We can, for some scenarios, we can count on fog and local compute, and without requiring the cloud at all, because cloud is expensive not only in terms of the network resources and the pipe to the cloud, but also in terms of monthly fees that should be paid to the cloud provider each month, or I don't know, according to how the deal is, but it's expensive. If we look at something like agriculture IoT, for example, or asset tracking, this may happen locally with a local solution without requiring any communication with the cloud. So fog computing comes with it adapts to the network infrastructure which exists. I mean, something like the IoT gateway, it is equipped with Wi-Fi connectivity, with Bluetooth connectivity, with cellular connectivity starting from 2G. I wouldn't speak about 5G right now, but it starts from 2G. And it has an Ethernet connectivity, and it can represent an enormous resources for compute, for processing, for storage. And so action can be taken directly here without going to the back-end cloud. So if we look at a solution counting on a back-end platform, which is not really a back-end, which is proximate to the sources of data and a low cost, versus a solution which requires continuous communication to the cloud. We are speaking also in the OpenFOC consortium on energy windmills, for example, as a very good use case for fog computing. So I believe in Egypt, if going to this question of fog computing interest in the region, that's another use case which can be very helpful in the area if we think about windmills and coupled with fog computing.